please feel free to share the screen. Thank you.
Okay, let me share my screen. Can you see my screen?
Yes. So I think we can start, and let me press the recording. Welcome everyone to Harvard CMSA Quantum Math and Physics Seminar Series. It is our great pleasure to invite Ruochen Ma from Perimeter Institute. And Ruochen currently is working with Chong, Wang, possibly Liujun at the PI, and he already done several interesting work related to quantum criticality, fractional insulator topological phases. Today, he will be speaking about edge physics at the deconfined transition between a quantum spin hole insulator and a superconductor. Let me remind the audience, please feel free to interact with Ruochen, and you can ask questions. Feel free. And so that's it. Let us welcome Ruochen. Oh, yes. Thank you.
Okay, thanks, Julian, for the invitation and the introduction. It's a great pleasure to be here for me. Today, I will talk about the edge physics at a quantum critical point between a quantum spin hole insulator and a superconductor. I will report on what I learned on this topic from my two mentors here, Liujun and Chong Wang, both at Perimeter Institute, and my reference is this paper with the archive number listed here. Okay, so let's start with an introduction to the deconfined quantum critical point in different systems. So the notion of the deconfined quantum critical point, or the original version, is a continuous or almost a continuous quantum phase transition, such that the phases on the two sides of the transition break very different symmetries. I will talk two different setup, and where it has been established that such kind of exotic quantum phase transition can happen. So the first example, probably the most well-known one, is the DQCP two-dimensional spin model. So for example, you may imagine a spin-and-a-half magnetic moment on a 2D square lattice. It does not have to be a square lattice, but the square lattice can be understood most easily. So you consider at each lattice site of the 2D square lattice, there is a spin-and-a-half magnetic moment. And the Hamiltonian can essentially be anything, but for simplicity, you can just imagine the simplest Heisenberg antiferromagnetic coupling, the SI.Sj term, plus some slightly more complicated spin interactions, which is the tuning parameter of the phase transition. And all the couplings, the whole Hamiltonian, is required to be invariant under some certain symmetry group, which I will describe shortly. And after you write down this Hamiltonian, you may ask yourself, what is the possible ground state of this Hamiltonian? And probably the most obvious one is the so-called Neel collinear magnetic order, in which the spins are arranged into this up-down pattern. So you can see this is just the Euro-Heisenberg antiferromagnetic order. And so in the Neel phase, the spin rotation symmetry, SO3 spin rotation symmetry, is broken spontaneously to a U1 subgroup, namely the spin rotation along the direction of the Neel order parameter. But by staring at the pattern, you can convince yourself that the C4 lattice rotation symmetry is unbroken in this pattern. So the relevant symmetry we will focus on in this phase transition is a SO3 spin rotation symmetry and a C4 lattice rotation with respect to each lattice site. And in the Neel phase, the spin symmetry is spontaneously broken to a subgroup, while the C4 lattice rotation is intact. And it turns out that by tuning some parameter, there is an alternative quantum phase, which is known as the valence-bond-solid phase, whose ground state wave function is look like this. And here, each ellipse represents a spin singlet formed by two adjacent spin-and-a-half moments. So each ellipse is a spin singlet. And you can look at the diagram, and you will convince yourself that here the spin symmetry is intact, since a singlet is invariant under a spin rotation symmetry, but the lattice rotation symmetry C4 is broken to nothing. So at each lattice site, you have to choose one out of the four directions to form a singlet. So you can see that these are two phases with very different symmetry breaking, such that the symmetry group in one of the phases, in either of the phases, is not the subgroup of the symmetry of the other phase. So naively, in the traditional lockdown second order phase transition scheme, you will conclude that you cannot have a direct continuous second order transition between these two phases. You have to go through some first order transition or some intermediate phase. But the interesting thing here is that due to the quantum nature of the spin, you actually can realize a direct, continuous, or almost a continuous transition between the two. And at the critical point, near the critical point, when the correlation length is large, you can go to the continuum, and the critical field theory is, for some historical reason, is known as the non-compact CP1 model. So it is a field theory with two flavors of critical bosonic matter field coupled minimally to a U1 dynamical gauge field denoted by this little a. And the crucial thing is the symmetry property of the degrees of freedom in this field theory. Here, the critical boson denoted by this C alpha, alpha can be up and down, actually is in a spin-and-a-half representation of the spin symmetry. And the tuning parameter of this phase transition is this boson mass R. And we can realize the two phases described above, depending on the sign of this boson mass. Okay, I will kind of rederive this critical field theory in a slightly different setup in the following of my talk. So if you are not familiar with this field theory, don't worry. I will explain how to derive it and how to match the phase in detail later. So for now, let us first accept such kind of field theory. Okay, this is the traditional deconfined quantum critical point on 2D quantum spin model. And it is also established that such kind of exotic quantum phase transition can be realized in a very different setup. So here we consider a phase transition on a fermionic system between an S-wave superconductor and a quantum spin Hall insulator. So it turns out that on this system, very similar thing can happen. To be concrete, you may imagine a fermion Hoping problem on a honeycomb lattice. Again, it does not have to be a honeycomb lattice, but previous numerical studies tell us that on a honeycomb lattice, you can write down some simple model that does the job to realize this phase transition. And the local operator here in the field, in the theory, in the model, is a spin-and-a-half fermionic electron operator. And we imagine the fermion can hope on the honeycomb lattice. So the electron operator is denoted by this C alpha, and alpha can be up and down. So it is in a spin-and-a-half representation of the SU2 spin rotation symmetry. And another relevant symmetry we will also focus on is the U1 global charge conservation symmetry, together with a time reversal symmetry. For the purpose of my talk, I won't talk too much about time reversal symmetry. So first, let us first focus on this part of the symmetry group, namely the spin rotation symmetry and the global U1 charge conservation. And of course, if you are careful enough, you should also note out the common Z2 center of this two symmetry group as the common center acts in the same way on the physical operators, namely the electron operators. And so there are two possible phases that we will focus on. So the first possible phase is a S-wave superconductor by tuning some lattice parameter, some interaction parameter on the lattice, you can realize a S-wave superconductor on this lattice model. It is a traditional S-wave superconductor. So the Cooper pair is a spin-singlet. It is invariant under the SU2 spin rotation symmetry. So the SU2 spin is preserved in the superconductor phase. But obviously, the U1 charge conservation symmetry is broken down to a Z2 subgroup, namely the fermion parity. And this is one possible phase of this model. So for the purpose of this talk, we will focus on this part of the talk and this phase transition. So the superconductor is shown here. And there is another possible phase, which we will call spontaneous quantum spin Hall insulator. So the conventional quantum spin Hall insulator, let's say the K and Malay model, can be fully understood in terms of a free fermion and band theory. But there, for example, in the K and Malay model, the SU2 spin rotation symmetry is broken explicitly down to a U1 subgroup by spin-orbit coupling. Here, however, on our microscopic model, there is no spin-orbit coupling, and we have the full SU2 spin rotation symmetry. But what can happen here is that the spin symmetry can be broken spontaneously to a U1 subgroup. Let's see the rotation along the z-axis. That is not very important. That's basically a basis choice. And combined with the remaining charge conservation symmetry, we have a U1, roughly a U1 cross U1 symmetry, and a quantum spin Hall insulator is protected. So we call this phase a spontaneous quantum spin Hall insulator, simply because here the SU2 spin symmetry is broken spontaneously. Okay.
Question. Great presentation. Very clear so far. Very nice. I enjoy it so far. Just question about, make sure the order on the quantum spin Hall side, you will regard it as a SPT phases protected by some U1 and also the U1 spin symmetry and time reversal symmetry, correct? Yeah. So you need invertible phases, invertible TQFT on the right hand side. And for the superconductor, do you want to consider this as a Z2 gauge theory with a dynamical Z2 gauge field, or just a Z2 global symmetry? Then you break down U1.
No, I will consider it as a phase with a remaining Z2 global symmetry, the fermion parity.
No problem. Great. And you say time reversal somehow will not play important role at the lambda Z2 transition?
So I will talk about the time reversal property at the end of the talk regarding some kinematic constraints, the anomaly of this phase transition. But for the two phases, to distinguish the two phases, time reversal is not so important, since here the two phases are all compatible with time reversal symmetry. So to distinguish the two phases, I just described these two symmetry, but it turns out that time reversal is also important. But for the simplicity, I don't plan to talk too much. But the time reversal is preserved throughout the phase diagram.
And can you comment about the lambda C1 transition to the semi-metal?
Oh, okay. This transition is so in my knowledge, this one, I don't have a very understanding if there is a good field theory to describe this phase transition. But on the lattice model, if you do some mean field theory or if you do some numerical calculation, you can observe such a phase here.
And what's a relevant deformation or all the parameter maybe is already shown somewhere by using this slide. Can you say a few words?
Okay. So there is only one relevant parameter, which is the tuning parameter of the transition, and I will comment shortly. This is in the field theory. This is the Boson mass, and all other possible relevant deformation are forbidden by the global symmetry of the problem.
Okay. Maybe should I start at least maybe written, but semi-metal phase, you may have some fermions, massless fermions.
Yeah.
And you pair them in some way to get quantum spin hole? Or you get a gap phase in quantum spin hole. So I suppose you pair some way, but is that pairing?
To be honest, I forgot about the detail of that transition.
That's right. So forget about that.
And you can check the detail of that phase transition in this reference.
Yeah, no problem. Thanks.
Sorry, I forgot about the detail of this part of the transition.
No worry. Sorry. Thank you.
Sure. Okay, other questions? Okay, great. Okay, and as Ruochen described just now, the SPT, the quantum spin Hall insulator, which is an SPT phase protected by a U1 cross U1 symmetry, has gapless edge fermion itself. So when the system have a boundary, there is a picture here showing the edge mode of the quantum spin Hall SPT. So in this case, the edge mode is a pair of helical gapless fermion. You have a right mover and a left mover, and there is no scattering between them since they carry different spin quantum number. For example, the left mover here carries spin up, and the right mover here carries spin down. So the spin symmetry forbids the scattering between these two fermionic edge modes. And so, yeah, it has been established that such kind of phase transition can be realized in the bulk, and the criticality is roughly the same as that one realized in the quantum spin model, and this was proposed by Grower and Sinto in 2008. But the question is that what about the edge? Since, as I just described, in the quantum spin Hall insulator as an SPT phase, it has some gapless edge mode. So it's natural to ask about the fate of this edge mode at the phase transition. So essentially, what we are asking about is the fermion gap. First of all, in the bulk of the phase transition, in the superconductor side and on the quantum spin Hall side, the gap of a single physical electron is finite and non-vanishing. That is obvious. And I will describe shortly that even at the phase transition, where the bulk spectrum is gapless, actually there a single electron is also gapped. So in the bulk, a single electron gap, a single fermion gap is always finite throughout the phase diagram. And the question is about the edge. We know that in the quantum spin Hall insulator, there is a pair of gapless helical mode. So on the quantum spin Hall side, on the edge, the fermion gap, the single fermion gap, is 0. But on the superconductor side, there is a non-vanishing single fermion gap, even at the edge. So as the transition is continuous or almost continuous, we kind of expect that the fermion gap should also change continuously, which means that even at the transition, there is some fingerprint of the gapless edge fermion in the quantum spin Hall insulator left. Even now, the bulk is gapless. So the natural question to ask is that, are there any remnants of the quantum spin Hall edge modes at the phase transition? And the interesting thing is that, so at the phase transition, we know that we have a full SU2 spin rotation symmetry and a U1 charge conservation symmetry. So if at the edge, there is indeed some remnants of the quantum spin Hall edge mode at the phase transition, then it could be viewed as some SU2 invariant analog of the quantum spin Hall insulator, which is known to be impossible if the bulk is gapped. This is the familiar statement that a topological insulator requires spin orbital coupling. And moreover, unlike the case of a quantum spin model, where part of the relevant symmetry, namely the C4 lattice rotation symmetry, is realized as a lattice symmetry, which is not so well defined on the edge. Here, all the global symmetry we will focus on, namely the SU2 spin rotation symmetry and U1 charge conservation symmetry, are realized in an on-site manner. So it's more clear to talk about the symmetry of the edge at the phase transition. So a natural question to ask is that, does this on-site manner of symmetry realization require any certain type of edge modes? And if we have some edge mode, then what is the quantum number of this type of edge modes? What is the nature of this edge mode? And there is a rigorous argument based on the notion of emergent anomaly. So regarding this problem, you can check a remarkable study listed here. The results based on the argument of emergent anomaly is that at the phase transition at the edge, if the full symmetry group, the SU2 spin symmetry, and the charge conservation is preserved, then a single fermion gap must vanish on the edge. And I will give a rigorous mathematical proof and some arguments based on anomaly at the end of my talk. So before I enter the detail, are there any questions about the introduction and the setup?
Yes, very nice. Let me just make sure that what you say. So you will discuss the age transition, and should I regard on the quantum spin Hall side, it will just be age base of a SPT or invertible TQT. And while on the superconductor age side will be no SPT.
Yeah. It's a conventional S-wave superconductor, and the edge is trivially gapped.
Right, no problem.
Okay, thanks for the question. Are there any questions?
Conversal symmetry will all be preserved on two sides.
Yeah.
And U1 charge conservation will be broken on the superconductor, but preserved in the quantum spin Hall.
Exactly.
And U1 spin symmetry is preserved both in the superconductor and the quantum spin Hall. But in the superconductor side, U1 will be enlarged to SU2.
So in the superconductor, the U1 charge conservation is broken to fermion parity.
Right, but U1's, I say U1 spin symmetry will be enlarged to SU2.
So it's an S-wave superconductor, so you have the full SU2 spin rotation symmetry.
Yes.
Mhm.
Yeah, agree with what I said. No problem. Thanks.
Okay, let me enter the formalism. So I want to first present a field theory of the phase transition. And so if you want to write down a field theory, the crucial first step is always to identify the appropriate degree of freedom. And here the principle is that the first, we can easily access both phases of the transition using the field theory. Namely, we can easily access the quantum spin Hall insulator and the superconductor. And the second principle is that we want to write down a field theory that can help us to somehow separate out the appropriate, the right degree of freedom at the edge, which can be used as a good start point for the following perturbation theory. So this consideration motivates the following important construction. And we simply rewrite the physical electron operator, which is a spin doublet, as a product of a bosonic parton B and a fermionic parton F in this matrix product form. And by staring at the parton construction, you can convince yourself that in this construction, there is an SU2 gauge redundancy. So if we rotate the B boson, the matrix B, by an SU2 rotation from the right, and the same SU2 rotation with a dagger to F on the left, the physical operator, namely the electron operator, is unchanged. So we have an SU2 gauge symmetry. And for the purpose of my talk, we actually only need a U1 subgroup of this SU2 gauge symmetry. So we will always consider a mean field ansatz of the F fermion such that the SU2 gauge redundancy is broken or Higgsed to a U1 subgroup. So in the basis we choose, the remaining U1 subgroup, the U1 gauge symmetry, is simply a phase rotation on the bosons and on the fermion, but with a opposite sign. So at the low energy, naturally, you will have a U1 dynamical gauge field denoted by this little a, coupled minimally to the two parton field B and F, but with opposite gauge charge, as you can see from the transformation rule here. Okay, this.
Sorry, Wilson, one quick confirmation. The indices 1 and 2, are they the two sublattices and a honeycomb lattice?
Oh, sorry. So here it should be regarded as the spin index. It is the spin index.
Oh, this is spin indices.
Yeah. So the fermion is the electron is a spin doublet, and you can regard it as a spin up and a spin down. Okay.
Yep.
This is our gauge symmetry. So as I said, we also care about the global symmetry of this phase transition. And now we examine how the global symmetries acts on the parton field. And for the U1 global charge conservation, the consistent way to assign the global charge is that the B field, the B boson field transform trivially under the global U1 charge conservation, while the fermion is rotated by a phase. So here you can see that here the parton construction is such that in the in the F parton, it is F1 and F2 dagger. So if the F parton is rotated by a U1 phase, then the F1 and F2 gets a opposite U1 phase. So here you should note that F1 and F2 carry the same gauge charge, but a different global U1 charge. And the B boson carries no global U1 charge. And this is the charge conservation. And under the SU2 spin rotation symmetry, so the symmetry assignment is that the B boson, the matrix B, is rotated by an SU2 matrix from the left. Note that the gauge rotation on B is from the right. Here, the SU2 global symmetry, a global spin symmetry, is acted from the left on the boson field, and the fermion field is transformed trivially under the spin rotation symmetry. And the time reversal symmetry acts on the parton field as this. So for the boson field, it's simply a complex conjugation, and the fermion field is a doublet. And for the purpose of my talk, I won't talk too much about time reversal symmetry. So the only important thing here is that time reversal symmetry is anti-unitary symmetry that scores to the fermion parity in the model. Okay. This is the transformation rule of the global symmetry. Any questions?
Sorry, yes, one quick one. So your F particle still has a spin index, right, which you denote 1 or 2. And yet the statement, right? So right.
It's a doublet, but it does not transform under the global spin rotation symmetry.
I see. So should I think of it as like a charge on something that doesn't carry the physical spin?
Yeah. Actually, it is charged under the SU2 gauge redundancy, but however, we've already hit it to a U1, and it does not carry the global spin charge.
Right. So if you for now only concentrate on global symmetries, would it be correct to say that F carries a global U1, so it's like a charged under the global electromagnetic field, whereas but at the same time it doesn't carry any spin. So you essentially moved all the spin indices onto the boson.
Exactly.
Thanks.
Yeah. So in the following, I will also sometimes couple the U1 charge conservation symmetry to a background gauge field, which is denoted as this capital A. And this is simply the physical electromagnetic field. Thanks for the reminder. Okay, now, if no questions, we shall move on. So now we have our kinematic setup. This allows us to describe both the quantum spin Hall insulator and the superconductor phase straightforwardly. So the key step is to arrange a mean field ansatz for the F fermion, such that the F1 fermion forms a chain insulator with chain number +1, while the F2 parton forms a chain insulator with chain number -1. And they will stay unchanged throughout the entire phase diagram. So since the fermions are gapped at the low energy, we can simply integrate it out. And the resulting response, field theory response, is this Chern-Simons term. Here, the U1 level 1 comes from the chain number 1 band, and the U1 level -1 comes from the chain number -1 band. And as I said, the two parton carries the same gauge charge but opposite global U1 charge. So after some algebra, you will get the contribution of the fermionic parton to your low energy response theory. That is simply a mutual Chern-Simons term between this capital A global background gauge field and this dynamical U1 gauge field. And for the B boson, as a boson, there are two possibilities. It can either condense or be gapped out. So the first possibility is that B condenses up to a gauge transformation or some basis choice. We can always choose the B1 to condense with a real non-vanishing vacuum expectation value, but B2 does not condense. It is simply a gauge choice, and you can always achieve that by a gauge rotation. And let me first remind you that the B boson does not carry the global U1 charge. So the global U1 charge is carried by the fermionic parton. So the condense does not break the global U1 charge conservation. The U1C is intact here. But however, since the boson carries the SU2 spin rotation symmetry charge, so the spin rotation is broken down to a U1 subgroup. Let's see the U1Z. So to see this, maybe probably the most easy way is that if the B1 has a real non-vanishing vacuum expectation value, then here the B matrix is simply a proportional to the identity matrix, and the remaining spin symmetry that is not broken is simply the SC rotation generated by the Z component of this matrix, and it is not broken since it can be cured by a gauge rotation from the right. So here the SU2 spin rotation symmetry is broken down to a U1 subgroup, and we have a condensation, and this condensation is charged under this U1 dynamical gauge field. So at the low energy, the little a gauge field is Higgs, and we can forget about it. So moreover, the physical fermion now can be identified with the F parton, with a renormalized quasi-particle residue, which is the vacuum expectation value of this B boson. And what is the resulting phase? So the resulting phase is simply a quantum spin Hall insulator formed by the physical electron due to the chain number of the F fermion. So you can see easily from here, that the physical fermion is roughly identified with the F parton, and the F1 which now carries a spin up, has chain number +1, and the spin down electron, which is roughly now F2, is in a chain band with chain number -1. So this state is simply the quantum spin Hall insulator. And the second possibility is that B is gapped out. So if B is gapped out, then at the low energy, we can simply integrate it out, which generates a Maxwell term for the dynamical U1 gauge field here. And combined with the contribution from the fermion F, we have such a low energy effective response theory, as shown here. And it turns out that this effective low energy theory describes an S-wave superconductor. So to see this, note that the coefficient of this mutual Chern-Simons term is such that a strength-1 magnetic monopole of this little a gauge field, which creates 2 pi flux of little a, and carries 2 units of global U1 charge. So it's simply a Cooper pair. And it's well known that in 2+1D, a Maxwell photon phase is a condensation of the magnetic monopole of this little a gauge field. So the monopole has a non-vanishing vacuum expectation value, and the photon itself can be viewed as the Goldstone boson for this monopole condensation. This is the famous Polyakov duality. And you can check Xiaogang or Subier, their textbook, and there is a detailed explanation of this. So as I said now, you have a condensation of magnetic monopole, and each magnetic monopole carries 2 units of global U1 charge. So now the global U1 charge conservation symmetry is broken down to a U1 subgroup, namely the fermion parity. And the monopole carries no spin quantum number, so it is simply a spin-singlet S-wave superconductor. So this is the description of our 2 neighboring phases of the transition. So what we now have is too complicated way to describe some already well-known phase. But the good thing is that now the transition can be described quite straightforwardly in this setup. So the transition happens when the boson is tuned to critical. And the critical theory, you can write down with the degree of freedom we use, the parton degrees of freedom, and the critical degree of the critical theory is simply this non-compact CP1 theory, roughly the same as the case in the quantum spin model. And the tuning parameter here is the boson mass. The boson can condense or be gapped out depending on the sign of this boson mass. And roughly it's just the same theory as the Neel VBS transition and in the bulk. And moreover, note that here, the physical electron, a physical fermion, is always gapped throughout the phase diagram, even at the phase transition. And the most easy way to see this is that here, the physical electron is a product of 2 sectors, B and F. And here the F fermion is always gapped with a exponentially decaying correlation function. So the fermion is actually gapped even at the phase transition where the bulk spectrum is gapless. Okay.
Excuse me, just make sure. Earlier, you described the condensation of the big B was maybe the B1, one of them is non-zero, but the other is 0. Maybe B1 non-zero and B2 0. And how about the other one? Maybe they're the same phase, so maybe different.
So you mean the okay? You can always bring your condensation pattern into this form by a, for example, global SU2 rotation. So it's simply a basis choice.
Okay, so they are in the same phase.
Yeah, they are in the same phase.
Oh, thanks.
Okay. Okay, now let's move on to the edge, which is the interesting part. So F fermion is gapped in the bulk, but since it is a chain insulator, it leads to gapless helical fermion at the edge. So as drawn here, there is a left-moving fermion coupled to A minus A, and a right-moving fermion coupled to A plus A. As I said before, the 2 parton carry the same gate charge, but opposite global charge. So they are the contribution of the chain band of the F fermion to the boundary theory. And to facilitate the following discussion on the edge dynamics, we can bosonize the helical edge fermions and end up with an edge Luttinger liquid. So you have 2 mutually do compact bosons and with a edge Luttinger parameter. which determines the scaling dimension of various operators, as we will discuss shortly. And you can also match the operators. For example, here the left moving and right moving helical mode is identified with the vertex operator of the edge Luttinger liquid, as written here. And an important thing is to match the two U1 symmetry of the Luttinger liquid with the U1 symmetries in our theory. So here, the Luttinger liquid has two U1 symmetry. One of them shifts here the phi boson by a constant. It is identified as the U1 gauge symmetry coupled to the little a field. And the other U1 symmetry of the Luttinger liquid, namely the one that shifts the theta boson by a constant, is identified with our U1 charge symmetry, the global symmetry. Okay, this is the contribution from the F fermion to the edge theory, but there are also the B bosons and the dynamical U1 gauge fields, little a, and they already have extremely non-trivial dynamics in the log. So to fully understand the edge dynamics, we have to consider all the possible symmetry allowed and gauge invariant couplings between the bulk and the edge. And there are a lot of possible couplings. To see how they can influence the edge dynamics, we consider a generalization to a large number of bosonic matter flavors. So a good thing is that the observables in the IR, if we consider a large generalization, can be computed perturbatively order by order in 1/n. So since it is a strongly coupled theory in the IR, we have to think about some kind of generalization. For example, here the 1/n generalization, and it gives you a small parameter which you can control the perturbative calculation in the IR. And I will describe the detail of the Liujun calculation in a second, but I want to first give you some physical intuition. So the result is that if we consider the n goes to infinity limit, the edge Luttinger liquid decouples dynamically with the critical bulk theory. And so it survives, the edge Luttinger liquid survives even at the critical point. And at the edge, the dynamical U1 gauge field little a only imposes a gauge invariant constraint for local operators, and it has no dynamical consequence. So it only tells you that which operator is gauge invariant local operator and which is not.
One question.
Mm-hmm.
So, but this boson, the boson field you get here is from some parton description, right?
Right.
So, in the Liujun limit, how can I relate this boson field to your original parton construction?
Good question. So now, if I consider CPn-1 instead of CP1, so this the spin symmetry is somehow, so now you have a SUN flavor symmetry, roughly an SUN flavor symmetry, but not the SU2 symmetry. But you can, but the SUN symmetry somehow reduced to the SUN, reduced to the SU2 subgroup when n goes to 2. Or you can consider that the SU2 is a subgroup that embeds in this SUN flavor symmetry. Oh, I'll show the filter.
But then the SU2 gauge structure this SU2 gauge structure you get from the parton construction where you have an SU2 fermion to begin with. So are you So in this large N limit, are you going to assume that the fermion are just, they are the same as these SU2 fermion, and you still have these F1 and F2, but there's no other fermions?
The flavor of fermion remains unchanged in this large N generalization. So if you want, actually, you can consider a slightly different parton construction, and where you choose an SU2 subgroup out of the B bosons, and okay, I should not describe it like that. So actually, the setup is that the fermion flavor remains unchanged in this in this large N generalization. You can see that it is a treatment for this critical field theory, but maybe it will be clear after I show you the theory. Maybe I should after I show you the field theory.
Yeah, thank you.
Any other questions? Yes, thanks for the reminder. So a crucial thing is that the fermion flavor is unchanged in this large N generalization, and we only consider a large N limit of the flavor of the B boson.
So Wilson, that last remark, that's kind of tricky to do the way you formulated it, right? Because you wrote it as a matrix product, and the number of components of F is the same as B by design.
Mm-hmm.
So how, sorry to press you on this a little more, but how are you going to achieve what you said in words? How can you have number of boson? I mean, maybe you could go to the matrix equation that you have for the ansatz.
Mm-hmm.
Yes, so if I look at this, how could you have the number of components of the F field not to be equal to the number of B fields?
Actually, at that limit, I consider it is a treatment for the dynamics of a critical theory, but not a generalization of a parton construction.
I see. So you're not going to do it in the bulk. You're just going to postulate that somehow on the boundary you have n flavors of bosons.
So you first write down a parton construction and end up with a critical field theory. And now you want to analyze the critical theory, the dynamics of this critical theory. And you know that in the IR, the theory, the dynamics of the theory is strongly coupled, and you need to consider some generalization. And at this step, I forgot about the parton construction completely and just treat the critical field theory and look at its dynamics.
I see. So maybe what saves the day for you is that the critical theory does not involve F's complete at all, right? It only involves the boson B. Is that what saves the day? That allows.
So at the edge, there is a contribution from the F fermion, but in the bulk, as you said, it is gapped.
I mean, so very specifically, when you write down the Luttinger liquid equation, right?
Yeah.
The theta and phi, the fields that enter there, are they describing B degrees of freedom or also F, the pseudo-fermions?
So the Luttinger liquid is from the contribution of fermion, and we need to consider the bosons separately. It is not from the boson; it's just from the two helical fermions resulting from the trim band of the F fermion.
I see. I mean, I suppose what's puzzling is that usually when you write down the spinful Luttinger liquid, you will have two copies of it. And you could label them in your notation by index 1 and 2, corresponding to the two flavors, right? And then you could formulate the spin charge separation, where you could see that the symmetric and anti-symmetric components of that would have different velocities, right? That's conventionally how you would do it. So that's why I'm asking for precision here. When you write down phi and cetas, the Luttinger liquid fields, are they only charge degree of freedom, or do they also carry spin?
You mean the Luttinger liquid?
Correct.
They don't carry spin. They don't carry spin. So the Luttinger liquid, the two compact boson here has two U1 symmetry, and one of them is identified with the charge conservation, and the other is the dynamical U1 gauge field, but not the spin rotation symmetry.
Okay,
sorry, give me a second.
Yeah, no, that's fine. That answers my question.
Sorry.
Yeah, no worries. That answers my question.
And another justification is that actually at the IR, we don't consider an SU2 gauge structure. And at the IR, the only relevant gauge structure is the U1. And all the other gauge group is, all the other part of the gauge group is completely fixed, and you can forget about it in the IR. And there's only a U1 subgroup. And if you work with this U1 subgroup, you can somehow write down some similar parton construction, but that's not essential. Okay. If there are no other questions, let me move forward. Okay, so as I already said, there are the B boson and the dynamical U1 gauge field little a, and they already have very non-trivial dynamics in the bulk. And the relevant question is that, what is the proper boundary condition of this bulk field? So for the boson, it turns out that the appropriate boundary condition is the Dirichlet boundary condition, also known as the ordinary boundary condition. So, which means that I require the boson field to vanish on the edge of the system. The reason is that in 2+1D, the Dirichlet boundary condition or the ordinary boundary condition is the only appropriate boundary condition when we consider the Liujun limits, and I'll explain shortly. And then is the dynamical gauge field little a. So up to a gauge choice, it turns out that we can also take the Dirichlet boundary condition. So which means the gauge field vanishes on the boundary. And this is a direct consequence of the Dirichlet boundary condition of the boson field. So remember that in the Euro-Liujun theory of a CPn-1 model in dimensions less than 4, the photon dynamics is induced by the B bosons. So if we consider a Dirichlet boundary condition of the boson field, then a direct consequence is that the gauge field also has a Dirichlet boundary condition up to a gauge choice. Okay, let me write down the theory explicitly. So instead of the CP1 model, we now consider a CPn-1 model. So you have n flavors of critical boson coupled minimally to the dynamical U1 gauge field little a considered above. And roughly there is an SUN or more rigorously PSUN flavor symmetry rotating this boson field. And for now, we only consider the n goes to infinite limits. And it turns out that even there, the edge dynamics still have something very, very interesting. So a well-known result is that when you consider a Liujun, so the gauge field is essentially dead. The gauge field is quenched at Liujun. This is basically because the photon propagator is of order 1/n. So recall that the effective photon propagator, which is the red wavy line here, is obtained by summing geometric series of bubble diagrams shown here. And on the bubble, there are propagating bosons. And each bubble comes with a factor of n. And moreover, in all dimensions less than 4, the boson diagram dominates the Maxwell term at the low energy. So we can completely forget about the Maxwell term at the tree level. And at the end, the effective photon propagator is essentially 1 over the bubble, which gives you the order 1 over n. So if you consider the n goes to infinity limits, the gauge field is quenched. And as a result, the B boson has exactly the same dynamics as a O2 and Wilson-Fisher boson. Since here you have an n flavor of a complex boson and they are equivalent to 2 n flavors of a real boson. So now the dynamics of the boson field is the same as O2 and Wilson-Fisher boson. And we can completely forget about the gauge field, except for the gauge invariant constraints imposed by it. And for the Wilson-Fisher boson at large n, in 2 plus 1D, I mean the bulk dimension, the boundary only has the ordinary universality class. So namely, now the boundary condition only has the ordinary transition. And this can be understood physically by noting that in 2 plus 1D, the boundary does not order when the bulk is disordered due to the Fermion-Wagner constraint. So the ordinary universality class means that the boundary is gapped and disordered throughout the bulk, this disordered phase, and ordered together with the bulk. And due to the Fermion-Wagner constraints, in 2 plus 1D, the order cannot order before the bulk. And there are some more complicated issue when n is small, but we don't need to worry about when n is large. So we only need to consider the ordinary universality class at the large n limit. And this justifies the Dirichlet boundary condition for the boson field. And as pointed by the question of Dan, you can consider that roughly the SUN flavor symmetry of the boson somehow reduced to the SU2 spin rotation when n is reduced to 2. But now we only consider the large n limits. And the boundary scaling dimensions for various operator are listed here. For example, the scaling dimension of a single boson, a single Wilson-Fisher boson in the O2 vector representation has edge scaling dimension 1. And remember that in the bulk, a single boson has scaling dimension 1/2, and the same as the Gaussian fixed points. And there are some other scaling dimensions for the edge operators, and two crucial edge scaling dimensions are the scaling dimension of the SU1 singlet at the edge, and the scaling dimension of the descendant of the U1 dynamical gauge field at the edge. And one of them has dimension 3, and the other has edge dimension 2. And the intuition is that here they have huge edge scaling dimensions, much larger than the scaling dimensions in the bulk. And this makes a lot of possible couplings between the edge and the bulk irrelevant and makes the problem tractable. So to study the possible coupling between the bulk and the boundary, we need to write down all the possible couplings allowed by the symmetry and the gauge invariance principle. So there are a lot of possible couplings. You have to write down all of them by brute force, and it's a a pretty boring exercise, and I won't list all of them. But I will explain some important ones. For example, here, the first term, this coupling, is simply the gauge coupling at the edge. So as I said, the shift symmetry of this B boson or the winding symmetry of the dual theta boson is coupled to this U1 dynamical gauge field. So the gauge coupling at the edge is something like this. The A mu field is coupled to the winding current of the theta boson. And as I said, the boundary descendant of the bulk dynamical U1 gauge field has scaling dimension 2. And as I conserve the currents of the edge, this part has scaling dimension 1. And remember that at the edge, now you only have 1 + 1 dimension. So a dimension 3 object is irrelevant, which means that now effectively at the Liujun limit, at the edge, the gauge coupling is effectively 0. And the Luttinger liquid behaves like a compact boson conformal field theory with a U1 cross U1 global symmetry. They have the same dynamics, but you have some gauge invariant constraints. And you can enumerate all the possible couplings, and it turns out that all of them are irrelevant at the Liujun limits. And if you consider finite n, all its scaling dimensions will receive some 1/n fraction, but the picture remains the same if the n is not too small. So, okay, what is the result? So the upshot of this analysis of this. Pardon?
Quick question. Very nice, thanks. Let me just ask. One of the boundary condition is familiar to me, the A = 0. So these are, I suppose, the bulk Wilson line, dynamical Wilson line can end on the boundary as dirichlet A = 0. And I wonder whether the other one also is from the bulk field B = 0 on the boundary. That one is some kind of a
okay.
Let me say both boundary condition give gap boundary, is that right? Or not? A = 0 should be gap boundary, I suppose.
So at the transition, the boundary spectrum is gapless. Okay, so here you need to consider, since here the boundary dynamics of the boson is same as a O2N Wilson-Fisher boson, and you need to ask yourself what's the possible boundary criticality of a Wilson-Fisher boson. And for an ordinary Wilson-Fisher boson, there are 3 possibilities: the ordinary phase boundary transition, the special transition, and the extraordinary phase transition. There are the 3 possible boundary criticality of a Wilson-Fisher boson. And for Liujun limits in 2 + 1 dimension, there is only one ordinary universality clause. So now forget about the gauge field, forget about the CP1 model, just consider O1 Wilson-Fisher boson in 2 + 1D, I mean the bulk dimension. And the edge, there are several different possible edge transitions when you consider, the ordering transition of the Wilson-Fisher boson. And when you consider the Liujun limits, only one out of these 3 is appropriate.
Actually, maybe let me just, sorry for, you are consider the age phase transitions, and on one side earlier you described the superconductor can have a gap age, and in fact, if you regard the superconductor as a Z2 gauge theory, there are 2 types of boundary conditions that you can choose A = 0 or the dual gauge field, let's say A tilde. The electric and magnetic gauge field can choose to be 0. Now these are electric or magnetic type of a gap boundary, but here maybe you are discussing near the transition. So possibly there are something more. I'm just trying to along thinking along the line of doing this age transition by maybe changing from the simpler a gap boundary, boundary conditions of choosing A or AT or die equal to 0 to the boundary condition you discussed. Are there some way relate those boundary to this one?
Okay, here you need to think about in the context or in the setup of large N. So here, I don't think the boundary condition for the gauge field is some like kinematic constraint. It is something imposed by the dynamics. So the gauge field, so first of all, at the large N limit, it is quenched. But for finite N, if the boson have Dirichlet boundary condition, then when N is large, if you consider the photon dynamics is induced by the boson bubbles, then it is also then the gauge field should also pick the Dirichlet boundary condition at the edge. This is imposed by this is a dynamical consequence, but not some from some kinematic constraints.
Okay. Yes, I think you are trying to answer. Let me just make sure. Are these boundary conditions compatible? The A and A equals 0 and the boson field B equals 0. Are they compatible or are they non-compatible? In the sense, are you setting the two together at the same time to define boundary conditions?
So I only set so it's really a complicated problem. So I first set the boundary condition of the B field, and it leads to the boundary condition of the A field at large N.
And they are compatible, right? You said it.
Right. They are compatible.
Okay. And the second one is due to dynamics to be consistent. Is that right? The second one.
Yeah.
Oh, sorry. Maybe the other. Which one is due to dynamics?
So this one is due to dynamics. This one is due to dynamics. And actually, this one is due to the dynamics of the Wilson-Fisher boson at large N.
Okay, great. Can you just remind us again, start from this boundary condition, how do you go to the superconductor edge side or to the quantum spin hole edge side?
Okay. So I think this is what I'll describe in the next slide.
Okay.
We first talk about some dynamics, and then it will soon become clear how to think about the edge physics. So are there any other questions?
Hi, Ruochen. Can I ask a few questions? First of all, is the Luttinger parameter on your edge tunable, or it's fixed by some symmetry?
Good. It's in my next slides. And if the boundary and the bulk decouples, then K remains as a exact marginal parameter.
But then it's tunable, right? Because
it's tunable. It's tunable.
Okay. Okay. And
you can
the second question. The second question is that you said the bulk boundary couplings are irrelevant even for small n. How small the n can be to keep it irrelevant? Because we know the rough scaling dimensions of those operators, right?
I think that's a rather difficult problem, since in my knowledge, the boundary critical behavior of a ON model is not completely clear. And so, but the rough idea is that so I think I don't have any good idea on this problem. So you need to carry out the 1 over n calculation and to see how it can influence.
Okay.
Scaling dimensions. Okay. And so these couplings are all irrelevant at the edge. So there are possible 1/n corrections, but the picture should remain the same for n not too small. And then due to this calculation, what is our IR theory? So the full theory in the IR is a critical bulk with Dirichlet boundary conditions for the bulk modes, plus a decoupled sector of edge Luttinger liquid with an exactly marginal parameter k, which means that somehow, or in some sense, the edge mode of the quantum spin Hall insulator survives at the phase transition, at least for n sufficiently large. And another observation is that the physical fermion, the single physical fermion B and F, which is a product of two decoupled gapless sector, is now gapless at the edge with power law correlation function. And with this knowledge, you can already calculate a lot of scaling dimensions of interesting operators on the edge, but probably the most entertaining one is the scaling dimension of a single physical electron, the fermion C at the transition. Since these two sector decouples, its scaling dimension is simply the summation of the B sector and the F sector. And the F sector can be calculated by this Luttinger parameter, and the B sector, as I listed above, is 1. So the boundary scaling dimension of this physical fermion is calculated here at the transition at the edge. And the most interesting thing is that now, if you look at this result, we look at the scaling dimension of a single fermion across the transition. On the side of the superconductor, the fermion, a single fermion is gapped. The edge does not have a gapless edge fermion, so effectively the edge scaling dimension of a single fermion is infinity, and we cannot talk about that. But on the quantum spin Hall side, there is a scaling dimension for an edge single fermion, which is determined entirely by this Luttinger parameter. And here you don't have a contribution from the bosonic sector, since in the quantum spin Hall insulator, the boson condenses, so the scaling dimension of the B field is 0, since it has long range order. So for quantum spin Hall insulator, the edge scaling dimension of a single fermion is completely determined by this Luttinger parameter. And the funny thing is that at the critical point, there is a universal jump in the fermion boundary scaling dimension. And here at the Liujun limit, the jump is 1 due to the scaling dimension of the boson. And for finite n, it may receive some order 1/n fraction, but the picture remains the same. The jump is universal in the sense that it does not depend on the Luttinger parameter. It is determined entirely by the property of the bulk CP n-1 field. And it is a direct manifestation of the spin charge separation at the phase transition at the edge. And after some calculation on dynamics, we now finish this talk by talking about some kinematic constraints. So it is the constraint imposed by the notion of emergent anomaly, and it requires that the fermion gap must vanish on the boundary. I'll first give a physical picture and followed by a rigorous mathematical proof. So consider we put the system on a disk geometry and turn on adiabatically a pi flux. So if we assume the physical fermion is gapped everywhere, then the flux can only induce a local excitation, since roughly it is the fermion parity. If the fermion is gapped everywhere, both in the bulk and on the edge, we already know that at the transition the fermion is gapped in the bulk, and if it is also gapped on the edge, then this flux is invisible from far away, and it can only induce a local excitation. But from the bulk deconfined quantum critical point, from the critical theory, we know that such a flux configuration traps a spin-a-half magnetic moment. The easiest way to see this is that if you turn on a flux pi, then it carries a unit of gauge charge, and to make it gauge invariant, you have to combine it with a gapless boson, which carries spin-a-half. So here, a pi flux carries spin-a-half. However, below the fermion gap, below the fermion gap, there is no local excitation with spin-a-half. So this is a contradiction. There must be something wrong with our assumption. And the contradiction requires that the fermion gap must be vanished at the edge, such that this flux pattern is visible by the edge fermion.
Sorry, Wilson, could you repeat again the argument for why inserting a pi flux should trap a spin-half?
Okay.
What I mean by this is, if I look at this Lagrangian, sorry, just hear me out. When I look at this Lagrangian, as you pointed out, the B fermion does not carry spin; it only carries charge.
The B fermion carries spin. So from the parton construction above, you can see that it carries spin, but not charge. It carries a gauge charge.
Yes, sorry, yes, I confused. Yes, you're right. Okay, B carries a spin, not charge. Yes, okay. So the fermion is gapped, B carries a spin, and hence the argument. Okay, perfect. Yeah, that's fine. Sorry for the confusion.
Thanks for the question. So after this this intuitive picture, let us give a mathematical proof, and this is should be the final slide of my talk. And so in the bulk deconfined quantum critical point, we know that the symmetry is realized in an anomalous manner, in the sense that the bulk transition can be viewed as a boundary theory of a symmetry protected topological phase in one higher dimension, with a topological action written here. So the physical meaning of this topological action is quite clear. So you may imagine a flux. You may imagine a pi flux of this U1 gauge field. You may imagine a pi flux of this U1 gauge field. So this part gives you 1. And you will find that it carries a spin doublet. It is a spin-a-half. This is the physical meaning of this topological term. And this should be considered as the topological term of the bulk SPT of this deconfined quantum critical point. Okay. So, and roughly, when we talk about an anomalous theory, it is realized as the boundary of a higher dimensional SPT. So it does not make sense to further talk about its own boundary, since a boundary of a boundary is empty. But in some cases, for example, the case here, if we want an anomalous theory, which is the deconfined quantum critical point, to really have a physical boundary, then there must be something at the edge to trivialize the anomaly, since the vacuum out of the boundary does not carry any anomaly. It is anomaly free. So there needs to be something happen at the edge to give you a consistent edge theory between an anomalous theory and the vacuum outside. Okay. So there are two common possibilities for this edge choice. The first one is the symmetry is broken at the edge. For example, in the context of quantum magnets, the boundary breaks the lattice rotation explicitly, which trivializes the anomaly at the edge. So there's no consistency at the edge, since part of the relevant symmetry is broken at the edge explicitly. And the second possibility is what we discussed here. So if the symmetry is preserved on the boundary, then there must be some kind of edge model with certain quantum number to trivialize the anomaly and give you a consistent edge theory. So, and what does the job here is the physical fermion. The physical fermion now has to become gapless at the edge and drive the critical theory into an anomaly-free theory. And it does this job by imposing a co-cycle condition like this. And here it can be regarded as some twisted version of spin structure. And you just plug this condition into this anomaly polynomial, and by some algebra, basically some Wu formula, and you will find that the anomaly polynomial is trivialized at the boundary by the gapless edge formula. So there's no consistency, and it requires that the fermion gap must be vanishing at the edge. And so the critical bulk with an anomalous realized symmetry actually enables a full SU2 symmetric version, a full SU2 symmetric analog of the quantum spin-Hall edge modes, a two anti-propagating Luttinger liquid. And this is impossible if you don't have a gapless bulk. So as a summary, we study the edge physics of the deconfined quantum critical point between a spontaneous quantum spin-Hall and an S-wave superconductor. And and at least in some generalization, Larsen generalization of the theory, we conclude that in this limit, the boundary Luttinger liquid in the quantum spin-Hall state somehow survives at the phase transition, but only at fractional degrees of freedom. And note that the F fermion only carry charge but not spin, global charge but not global spin. And there is a universal jump in the fermion, I mean the single physical fermion scaling dimension at the transition. And this is a direct manifestation of the spin charge separation at the deconfined quantum critical point. Okay, let me stop here.
Thank you very much, Ruochen. Question from the audience. I do have one, but the audience goes first.
I have a question. So yeah, very nice talk. So yeah, you show that from this large N calculation, you always get gapless fermion at the phase transition, and you also show this anomaly argument that tells you if for n equals 2, this gap you still have a gapless fermion. So my question is that this universal jump in fermion scaling dimension that is from the calculation of large N theory, right? So whether, is this universal jump depend on N?
It should depend on N. It should depend on. So to remember here, if you calculate finite N, you should remember some one-to-one correction. So I mean, here the universal is in the sense that it does not depend on the Luttinger parameter, but it does depend on N and the bulk property of the CP, the bosonic critical theory in the bulk.
And so how do you expect the Luttinger parameter and this scaling jump and this universal jump to change whether, and so if you include 1/n correction?
It should be modified. It should be modified. But so at sufficiently large n, where these two sectors are still decoupled, then this part, the jump, still comes from the boundary scaling dimension of the boson field.
Mm-hmm.
I mean the edge scaling dimension, the boundary scaling dimension.
Mm-hmm. I see. Thank you.
Mm-hmm. So you just need to calculate the edge scaling dimension of the CPN -1 model with the Dirichlet boundary condition to 1/n order, and you will know that. But it is very complicated. It would be very complicated. Some other questions?
Can you comment again about this universal jump of the fermion scaling dimension?
Yeah.
Maybe in a physical picture, what happens? Maybe you already say, but it's good to recap again. What's the physical picture when there's such jump? Why not, for example, change gradually?
Okay, so here, so if we expect that the bulk is decoupled from the boundary, then there's no reason that the Luttinger parameter K changes suddenly. So we expect K, the Luttinger parameter, changes continuously through the jump. But what changed the scaling dimension and gives the universal jump here is that now the contribution from the boundary scaling dimension of the boson field. So at the transition, you have a critical boson together with a fermion. And since they decouple, the boundary scaling dimension of a single fermion is the summation of these two. And if you look at the quantum spin Hall side, the B boson is condensed, right? This part is condensed. And it has long range order with scaling dimension 0. You can think about in this manner. Or you can just think about an edge Luttinger liquid. So now at quantum spin-off side, the bulk is fully gapped, and you only have a Luttinger liquid at the edge. And you simply calculate the scaling dimension of a single fermion using the Luttinger parameter. And it's given by this well-known result. And we expect that this Luttinger parameter to change smoothly at the phase transition. Since in some limit, these two sector decouples, and there's no reason to give you a sudden jump. And so the key point here is that if you approach the transition from the quantum spin Hall side, the B boson, it turns from condensation and to critical. Did I answer your question?
Sorry, I think I missed something you say. You say there's no reason for sudden jump for which one?
For the Luttinger parameter. For the Luttinger parameter.
But the scaling dimension does have some sudden jump.
Yeah.
And it is a sudden jump from both sides, right? From the superconductor side, also from.
Yeah. So here on the edge, for superconductor side, since the single fermion is gapped, so the scaling dimension is effectively infinity, right? So there's also a jump if you regard this part as with a scaling dimension infinity.
Okay, thank you. Any comments, question more? Let us thank Ruochen first.
Thank you very much.
Thank you, Luton.